Okay, I'm going to illustrate the idea of scaling a graph, of a four-plane graph, in terms of the problem we saw early in the course with the plot. And in this case, we're not going to solve the problem of the plot and the scale of the plot directly, but we're going to do something that's kind of relevant to that situation. And we're going to say that we've somehow determined that the area of a 1-inch square represents 3 acres. So let's say here's a plot. It's not a perfect square. And here is what's supposed to represent a perfect square. This is your 1-inch square. Kind of abbreviate that. That's our 1-inch square there. It's 1 inch by 1 inch. Okay, well, I want to draw a graph, first of all, representing the four-plane function. Now I'm going to start with a point here, and I'm going to move over to the point that's twice as close to the origin, then twice as close again, and twice as close again, and twice as close again. And I'm going to pick a value for this point, a point on the graph corresponding to this point. And that means I'm just going to pick a point on the coordinate system up here and declare that that point is going to be on my graph. Now, if this point is on my graph, then when I take half of my x value, I'm going to get 1/4 of the y value. Okay, now right now we're not talking about areas in acres and squares in inches. We're just constructing a four-plane graph. So I've got to take this y coordinate here and cut that in half. That puts us about here. Cut that in half. That puts us about here, which gives us a point over here. Then I'm going to move twice as close to the origin again, and that's going to cause the graph to decrease by another factor of 4. Now, why are we decreasing by a factor of 4? Well, it's because we're halving the x values. If y decreases by a factor of 4 when x becomes 1/2, then when we double x, we're going to get 4 times the y value. Okay, well, we can do that again. We can find a point that's 4 times as close to the origin as this one. That's going to bring us down about here. Now, if we keep halving this, as we've seen, we can keep halving as long as we want, and we can keep taking 1/4 of the y value as long as we want. And as we do so, we're going to approach the origin. Both x and y are going to approach 0. We can't really draw the y value that's 1/4 of this y value. The chalk lines are too thick. So we can construct our graph, and that graph isn't all that well constructed. I think this 1/4 is a little big. Yeah, this point should have been a little lower. The graph should have had a little more of a curvature. However, if you carefully scale the graph and draw it, you'll get a good representation of a y equals ax squared graph. So this is a graph of y equals ax squared. We don't know the value of a. Now we're going to put a scale on it. We're going to pick some point on the x-axis to represent 1 inch. Okay, so let's say that this point here represents 1 inch. That's our side length. Now, the area, of course, of a 1-inch square is 1 square inch. But we're going to use the acreage correspondence. So we're going to say that at 1 inch, the y-coordinate, instead of being 1 square inch, is going to represent 3 acres. So that we can now scale the rest of the graph. we have units of an inch. We come out another unit of an inch, we're here, and we're not doubling anymore, we're just coming out another unit of an inch, excuse me, each time, another inch here. So we're up to, and we can come out another one, we could even get another one, but up here we're up to 5 inches. So that X would be measured in inches. Y, on the other hand, well, here's 3 acres. Now if we come out another 3 acres, we're here. Come out another 3 acres, we're going to be here. Another 3 acres is going to put us here. So 3 acre increments will put us, I don't know if I'm keeping these increments constant. Maybe not doing too bad, but here's 3, 6, 9, 12, 15, 18, 21, 24, 27. Here's 30 acres. I'm going to kind of abbreviate that. That would be here. Okay, 15 would be 3, 6, 9, 12, 15. So here would be 15 acres. Chalk's a little soft, so it's a little hard to write that clearly. In any case, we have now a scale, and we could extend the scale, and of course we could draw it all much more accurately, where again 1 inch corresponds to 3 acres. That is, 1 square inch corresponds to 3 acres. A square of length 1 inch would correspond to 3 acres. So that a square of 2 inches would correspond, well, we can come up here and over here, and I estimate that to be around 10 acres, okay, 9 acres. 3 inches out here, come back over here, it looks like about 18 acres maybe. What we want to do is now write the function in terms of this A constant. We've got to figure out what A is so we can write out a function that would then allow us to, in fact, calculate the relative areas. Okay, now I've written this out off camera, but let's look at the logic of this. Y is 3 acres when X is 1 inch. We know that Y equals AX squared, so it follows that we plug in 3 acres for Y and 1 inch for X. We can solve to get the value of the constant A. So we say that 3 acres is A times the quantity 1 inch squared. A therefore equals 3 acres divided by the square of 1 inch. And the square of 1 inch is 1 inch squared. So we see that A is 3 acres per inch squared. It follows then that Y equals 3 acres per inch squared multiplied by X squared. Now this relabeling of the graph might or might not be useful in a given situation, but it gives us an option for figuring out the area that would correspond to this plat. Okay, for example, if I take this 1 inch square and construct a 2 inch square, it's going to have twice the width of the 1 inch square. 1, 2 times, so it's going to be about this wide. It's going to be twice this high, so it's going to be about 1, 2, about this high. And I can divide that into the square inches if I want to. It's not necessary to do so. Okay, the question is the area of this 2 inch square greater or less than the area of this plat, or is it pretty close? We can look at the parts of the plat that extend outside the square, and then we can look at the parts of the square that extend outside the plat and make a decision about which is bigger. Is there more area of the plat outside the square or more area of the square outside the plat? It looks to me like they're pretty close. So it looks to me like the area of this plat ought to correspond to a 2-inch square, if I project over the 2-inch square, it looks like I get something pretty close to, well, 369 acres. Now, if I calculate here, and that projection line actually looks like it's gone down toward the x-axis a little bit. If I projected it a little more accurately, it might actually come over to around somewhere between 9 and 12, maybe 10 or 11 acres. Of course, if I use the formula here, x is now 2 inches. If I square 2 inches, I get 4 inches squared. Multiply that by 3 acres per square inch, and I get 12 acres, which isn't exactly consistent with the graph. But remember, the graph is hand-drawn. A more accurate graph would result in a better estimate of the area of this plat. Writing a short summary of what I just said, 2-inch square corresponds to 11 acres by a graph estimate. Okay, if I go up here and across here, maybe it's 10, maybe it's 11. I think it is a little more than 9. Remember, this line needs to be parallel to this axis. And then, according to the model, the y equals 3 acres per inch squared times x squared. I substitute in 2 inches for x, and I get the value of y. If I square 2 inches, I get 4 inches squared. If I multiply 4 inches squared by 3 acres over inch squared divided by inch squared gives us just 1, divides out basically. 3 times 4 is 12, and we're left with 12 acres.